Welcome to this video on factors and multiples. Let's begin. First of all, what is a factor and what is a multiple? Let's first define factors. A factor of a number is a number that divides evenly, in other words with no remainder, into another number. So for example, we would say that 2 is a factor of 4. 4 divided by 2 is 2. We can also write a factorization tree that looks like this. Is 3 a factor of 4? Well, let's try. When we divide 4 by 3, notice we get 1, but we have also a remainder of 1. If you do long division like this, we can see that, again, 3 goes into 4 once, but again, we have 1 left over. So 3 is not a factor of 4. If we restrict our discussion to only positive numbers, the following statement is true. The factors of a number are less than or equal to the number itself. So let's think about the number 8. What are the factors of 8? Well, we kind of really just need to list our multiplication facts. Well, 8 times 1 is 8. So if we look on our number line, 8 and 1 are both factors of 8. What else multiplies up to 8? 2 times 4 also multiplies up to 8. So we see the numbers 4 and 2 are also factors of 8. Therefore, if we're listing the factors of 8, the factors of 8 are 1, 2, 4, and 8. Let's see if we can come to any conclusions about factors by looking at these numbers. So first of all, notice that all of these factors, 1, 2, 4, and 8, are less than or equal to the number itself. So we know that the largest factor of a number is the number itself. In other words, I can't have a factor of 8 that's larger than 8. That makes sense because when we're factoring things, we're breaking them down into smaller pieces. So again, the largest factor of the number is the number itself. A factor cannot be larger than itself. So the smallest factor of the number, notice, is 1. And this is true of any number. The smallest factor of a number is always 1. So again, the largest factor of any number is the number itself. The smallest factor of that number is 1. And then all the other values, of course, are somewhere in between 1 and the number. Every finite number has a finite number of factors. And if you think about it, this really makes sense. What we're doing when we're factoring is breaking numbers down into smaller and smaller bits until we can't break them down anymore. So let's look at 8. We can break it down into 4 times 2, and we could break that 4 down again into 2 times 2. But 2 is a special number, right? Why can't we break 2 down any further? Well, the reason that we can't break 2 down any further is because it's what's called a prime number. A prime number is any number larger than 1 that is only divisible by 1 and itself. So let's go through some numbers and practice identifying whether or not it's prime. So we already said that 2 is prime. It's 2 times 1. Nothing else goes into it, so it's prime. What about 3? Well, 3 is just 3 times 1. Nothing else goes into 3. What about 4? Well, 4 is 2 times 2. Therefore, we cannot say that 4 is a prime number. 4 is not prime because it's divisible by something besides itself and 1. What about 5? Well, 5 is just 5 times 1. No other number goes into 5, so it's prime. What about 6? Well, 6 is 2 times 3. 2 and 3 both go into 6, so it's divisible by more than just 1 and itself. Therefore, 6 is not prime. Let's keep going. 7 is just 7 times 1. Nothing else goes into 7, so it is prime. What about 8? Well, we already know that 8 isn't prime because it's divisible by 4 and by 2. What about 9? Well, 9 is 3 times 3. So again, 9 is not prime. What about 10? Well, 10 is 2 times 5. Definitely not prime. What about 11? 11 is just 11 times 1. Nothing else goes into 11, so it is prime. What about 12? Well, 12 is 4 times 3. It's also divisible by 6 and 2, so definitely not prime. 13 is prime. It's 13 times 1. Nothing else goes into 13. So at this point, you might be wondering, what is the largest prime number? Is there a highest prime number? Is there an upper limit on the number of prime numbers that exist? Well, according to Euclid's theorem, there are infinitely many prime numbers, so there is no largest prime. In fact, some people dedicate their whole PhDs. They spend years and years trying to find the largest prime number. If you Google what is the highest prime number, it will tell you, but it will also put a date by that because people are still looking for larger and larger prime numbers. They're still doing all this work and research. So take a minute, pause this video, and look it up. See what the highest prime number is, just out of curiosity, and see when it was most recently found. All right, let's keep going. So we're talking about prime numbers because we want to talk about prime factorization. Prime factorization is the process of breaking down any integer into a product of prime numbers. Now, a lot of times, people don't have their multiplication tables memorized. When I was growing up, I had to memorize it, and it's very helpful. However, if you don't know your times tables up through 10 times 10, then these rules can really help you know where to start factoring. So if you want to know if something is a multiple of 2, in other words, if 2 goes evenly into it, it is if it's an even number. Even numbers end in a 0, a 2, a 4, a 6, or an 8. What about multiples of 3? This is a little bit more tricky. So there's a fun trick to figure out if something is divisible by 3. And what we can do is we can sum its digits. When we add the digits of the number together, if that sum is divisible by 3, so is the number itself. So let's take the example of 1,236. That's a very large number, and you probably don't know off the top of your head if it's divisible by 3. So by summing the digits, I mean we're going to add the digit 1, 2, 3, and 6 together. When we do that, we get 12. Is 12 divisible by 3? It is. 12 divided by 3 is 4. So that means that this whole number, 1,236, is also divisible by 3. So you can use this little trick to help yourself if you're not sure if a number is or is not divisible by 3. What about 5? Well, if a number is a multiple of 5, or in other words, if it's divisible by 5, it will end in a 0 or a 5. And lastly, if a number is divisible by 10, it will end in a 0. So let's use this process of prime factorization to find the prime factorization of 54. So let's first look at multiples of 2. This ends in a 4, so we know that it's going to be divisible by 2. If you type that in your calculator, 54 divided by 2 is 27. Now 27 is an odd number, so it's definitely not divisible by 2. So let's move down to multiples of 3. Is 27 divisible by 3? Well, you might happen to know that 27 is 3 times 9, but if you don't, remember you can use the trick of adding 2 and 7 together. Well, 2 plus 7 is 9. 9 is divisible by 3, therefore 27 must be divisible by 3 as well. So in a calculator, you can type in 27 divided by 3, and we get 9. Okay, so 27 is 3 times 9, and then of course 9 can be broken down even further to 3. Okay, so how are we going to capture the prime factorization? Well, we need to go down and circle just the prime numbers. 3 is a prime number, so we circle all the 3's, and 2 is a prime number. Therefore, if we write the prime factorization of 54, it's 3 times 3 times 3 times 2. This is the prime factorization of 54. Prime factorization is one method, not the only method, but one method that can be used to find the greatest common factor of a set of numbers. So we've been talking this whole video about factors, but we haven't really talked anything about multiples. I mentioned them briefly when I was talking about the rules of looking for whether a number is divisible by something. So I did use that word, but I haven't really defined it. So let's define the word multiple. Well, we already know a factor is a number that divides evenly with no remainder into another number. So a multiples are numbers you get when you multiply a certain number by an integer. But what does that mean? Well, let's find out. Let's think about the factors and the multiples of the number 8. We've already talked about the factors of 8, haven't we? Right? We know that the factors of 8 are 2, 4, right? And we also know that 8 is 8 times 1. So let's put those on a number line. So the factors of 8 are 8, 1, 2, and 4. Okay? So those are the factors of 8, but what are the multiples of 8? Well, what does the word multiple sound like? The word multiple sounds like multiply, doesn't it? So to find the multiples of 8, we just keep multiplying 8 by different numbers. So in other words, 8 times 1 is 8. So the first multiple of 8 is itself, 8. Well, the second multiple of 8 is going to be 8 times 2, which is 16. The third multiple of 8 is going to be 8 times 3, which is 24. You might notice that I have conveniently labeled or numbered my number line by 8s, the multiples of 8. Okay, so let's look at this chart and kind of analyze what we see here. So if I'm looking for factors, notice that the factors of any number have to be less than or equal to the number itself. Also, remember we said that every finite number has a finite number of factors because there's really this hard line here at 1. 1 is going to be the smallest factor of any number. Okay, so we have this hard cutoff at 1. So we know two things. The factors are smaller than or equal to the number itself, and that we can have a finite number of factors, not an infinite number of factors. All right, so now let's think about multiples. So remember, the smallest multiple is the number itself, right? So again, 8 is the smallest multiple of 8. But what is the largest multiple of 8? As you can see, my little number line here, because my page is only so big, only goes up to 48. But I think we can all agree that since this is only 8 times 6, right, that I could probably keep going and get to 8 times 7. And because I can always add plus 1 plus 1 plus 1, right, there is no largest multiple. In fact, there are an infinite number of multiples for any number. So, to review, right, first we've learned that the factors of a number are less than or equal to the number itself, while the multiples are greater than or equal to the number. And again, this makes sense because we get the factors by dividing. When we divide by integers, by whole numbers, that makes numbers smaller, right? Multiples, we get multiples by multiplication, right? If I keep multiplying by whole numbers, 1, 2, 3, that's going to make numbers bigger, right? And there's not really an upper limit on infinity. Right, when we divide, remember, there is a lower limit, right, because we only go down to 1, right? 1 is going to be the lower limit of our factors. So we also know that every number has a finite number of factors, but an infinite number of multiples. So why do we care about factors and multiples? Well, a lot of times we have to find either the least common multiple or the least common denominator. Believe it or not, this is actually the same procedure. The only reason it has a different name is because when we find the least common multiple and it's in the denominator of a fraction, we call it the least common denominator. But if you know how to find the least common multiple, then you're going to know how to find the least common denominator. So, the least common multiple is always as large, at least as large, as the largest number. This follows from the fact that the multiples of a number have to be greater than or equal to the number itself. In other words, I can't say that 4 is a multiple of 8. I can't get 4 by multiplying 8 by 1 or by 2 or by 3, can I? To get 4 from 8, I'd have to multiply 8 by what? I'd have to multiply 8 by 1/2, but 1/2 isn't an integer. Okay, so 4 is not a multiple of 8. Remember, the multiples of a number are at least as big as the number itself or larger. So let's practice finding the least common multiple of 2 and 3. So a nice way to think about this is to think about a number line. So let's go through this number line and circle all of the multiples of 2 in orange. Well, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. And again, notice I very cleverly and conveniently numbered my number line on purpose as multiples of 2. So my work here is kind of already done for me. Now let's go through and circle the multiples of 3. Well, 3 times 1 is 3. Have to write that one in. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. Okay, so what do we have? We have a lot of options here, right? The numbers that are circled in both blue and orange are 6 and 12, and if we had gone on, we would have found more. However, we don't need to go on, right? Because we don't want all the common multiples, we just want the least common multiple. So really, we could have stopped when we found 6. 6 is the smallest or the least common multiple. Okay, so another way to understand what we're looking for is we're looking for a number that when we divide it by 2 gives us a whole number. So 6 divided by 2 is 3. 3 is a whole number. Also, 6 divided by 3 is 2. 2 is also a whole number. So this fits the bill. 6 is the smallest number that is evenly divisible by both 2 and 3. So we say that 6 is the least common multiple of these two numbers. Now we have 3 numbers to look at, 2, 3, and 5. So let's just have some fun with the number line. So you might think that I would start with 2 again. However, I'm going to show you a trick. Remember I said that the least common multiple has to be at least as large as what? Has to be at least as large as the largest number. So let's be lazy for a minute. Let's start with the multiples of 5. You might notice that I cleverly numbered my number line already with the multiples of 5 to make my life a lot easier. So these are all the multiples of 5. So I don't really care about the tick marks, right? Because obviously only the green circled numbers are going to satisfy the least common multiple. My least common multiple has to be one of these circled numbers. It can't be one of the uncircled numbers. Okay, so now let's go down in value. So now we're going to go down to 3. So which of these green circled numbers are also divisible by 3? Well, 5 isn't, 10 isn't, but 15 is. Okay, so let's keep going. 20 isn't, 25 isn't, 30 is, 35 isn't, 40 isn't, but 45 is. All right, so now remember we have this third number to worry about, which is the number 2. So let's circle all of the numbers here that are multiples of 2. Well, they're going to be all the even numbers. So that's 10, 20, 30, 40. All right, so which of these numbers, what's the very first number that you see that has been circled or that it is a multiple of all 3? Well, you probably noticed that it's 30. 10 is a multiple of 2 and 5, but not 3. 15 is a multiple of 3 and 5, but not 2. Likewise, 20 is a multiple of 2 and 5, but not 3. So 30 is the smallest number that fits this bill. Let's test it down here and prove to ourselves that it really works. Well, 30 divided by 2 is 15, which is a whole number. 30 divided by 3 is 10, still a whole number. 30 divided by 5 is 6, still a whole number. So 30 works. 30 is the smallest number that is evenly divisible by 2 and 3 and 5. What if we have 2 and 5 and 10? Again, I'm always going to start with the largest number. Why? Because I know that my least common multiple has to be at least that large. So, as you can see, again, I've already cleverly labeled all of, labeled my number line in in units of 10. So I've circled all of the 10, multiples of 10, sorry. All right, so now let's go down and circle all the multiples of 5. Well, all of these are also multiples of 5, aren't they? Huh, that's interesting. What about 2? Well, they're also all multiples of 2, aren't they? Wow, how interesting. All right, so now if I put 10 down here, again, just as a litmus test, make sure, right, that this really works. 10 divided by 2 is 5. 10 divided by 5 is 2. 10 divided by 10 is 1. So 10 is my least common multiple. It's the smallest number that's evenly divisible by 2 and 5 and 10. So I have a question for you. Is there any way that I could have figured that out without going through this copious and tedious process of drawing a number line? Is there a different way to think about these numbers? Well, the good news is that there is. Remember that thing I talked about before, the prime factorization? Prime factorization can help you build your least common multiple. So we already know that 2 is a prime number, so we're not going to mess with him. 5, also a prime number, so we don't want to mess with him. But what about 10? 10 is not a prime number. The multiples of 10 are 2 and 5, aren't they? So guess what, guys? This is the crazy part, right? By definition, if a number is a multiple of 10, by definition, it's also a multiple of 2, and it's also a multiple of 5, because 10 has 2 and 5 in it. So I could have known just by looking at this that the LCM is 10. Is there a different way to look at it? I think so. So another way to think about it is we can build our least common multiple. Okay? So what we're going to do is we're going to pick out the numbers that are up here that are represented just by the primes. Okay? So we have a 2 here and a 2 here. There's only one 2 in each of those places. I'm only going to write it once for my least common multiple. Okay? Then we also have a 5. We have a 5 here and here. It only occurs once in each of those places, so I only write it once. So basically, by this process, then we have 2 times 5 is 10. So this is another way to think about or find the least common multiple. And again, you can do this without using a number line. So notice now, right, I have this problem. I didn't create a number line, did I? Okay, so let's use that process of prime factorization. So 6 is 2 times 3. 24, this is going to take a little bit more work. 24 is 6 times 4. 6 is 2 times 3, right? 4 is 2 times 2. All right, guys, so let's see if we can go through the tedious process of building our least common multiple. Okay, so first I'm going to circle a 2. There's a 2 here and here. He goes in there once. Okay, what else do we have? Well, I have another 2 here, don't I? So I have to put him down. Then I have another 2 here. He has to go there. Then I have another 2. I'm running out of colors here. Oh, I don't have another 2. I'm sorry. I have a 3. So we'll put a 3 right there. And then last but not least, I have the 5. Okay, so this is going to be my LCM. It's 2 times 2 times 2 times 3 times 5. So you can type that in your calculator if you want. You get 120. So if I have 120 divided by 6, what does that give me? Well, it gives me 20. 120 divided by 5 is 24, and 120 divided by 24 is 5. Okay, so this works. It checks out. Is this the only way to think about this problem? It isn't. Let's think about it a different way. So let's think about the numbers 6 and 24. Did you notice that 6 is already a factor of 24? So by definition, right, if a number is a multiple of 24, it is also a multiple of 6. So I don't have to include this in my calculations. The 6 is already taken care of if I include the 24. So the only other thing that I have to include in my least common multiple is what? Well, it's this 5, right? There's no 5 over here anywhere in the 24. He does not have a 5. So I could just do 24 times 5. And lo and behold, that gives me 120. Again, this is just another way to understand the least common multiple. Let's do some more examples. So we have 2, 6, and 10. So let's do our prime factorization. 6 is 2 times 3, and 10 is 2 times 5. Let's build our least common multiple. I have a 2 here, and here, and here. So 2 has to go into my least common multiple. Then I also see that I have a 3. So 3 has to be part of my least common multiple. Okay, then we also have a 5. So 5 has to be a part of my least common multiple. So we have 2 times 3 times 5. That's 30. Let's test it and make sure that it works. 30 divided by 2 is 15. 30 divided by 6 is 5. 30 divided by 10 is 3. So all of these are evenly divisible. 30 is divisible by all of these numbers. Therefore, it is, in fact, the least common multiple. Let's do another number. At this point, I would strongly encourage you to pause this video, try this on your own, and then unpause it to see if you're correct. So all of these numbers are prime except for 4, which of course is 2 times 2. Remember what that means. That means that if a number is a multiple of 4, it's also going to be a multiple of 2. Isn't that what it means? Right? So when I'm building my least common multiple, I don't have to think about the 2 because the 4 is taking care of that. So I just have to take care of the 4, oops, sorry about that, and the 5. Well, what is 4 times 5? It's 20. So 20 divided by 5 is 4, 20 divided by 4 is 5, and 20 divided by 2 is 10. So again, it works. If you don't like this way of thinking, another way, an equally valid way of thinking about it, is to do our building blocks. So we have a 2 here, so the 2 has to go into our least common multiple. We have another 2 here, so he has to go in there as well, and then we have a 5. 2 times 5 is 20, so again, our least common multiple is 20. What about 12, 6, and 2? Again, pause the video, think about this, and see if you can figure it out. Then unpause it to see if you're correct. Well, notice that 12 is 6 times 2. So anything that's a multiple of 12 is also a multiple of 6. So the 6 is taken care of. And 12 is divisible by 2. Anything that is a multiple of 12 is also a multiple of 2. Therefore, our least common multiple is 12. Let's prove that this is true. 12 divided by 12 is 1. 12 divided by 6 is 2. And 12 divided by 2 is 6. Therefore, our least common multiple is 12. What about this one? We have 30, 5, and 7. Well, 30 is 6 times 5. So guess what? That means we don't have to worry about the 5. Because if something is a multiple of 5, it is also, by definition, a multiple of, if something is a multiple of 30, it is also, by definition, a multiple of 5. So, to find our LCM, we can just simply do 30 times 7, which is 210. So, let's test that theory and make sure that it works. So, 210 divided by 30 is 7. 210 divided by 5 is 42, and 210 divided by 7 is 30. So it definitely works. Again, if you don't like this method, another way to think about it is to do a prime factorization. 30 is 6 times 5, and 6 is 2 times 3. Okay, so when we're building our LCM, okay, we'll capture 2. He's only in one place. Then we'll capture 3. He's only in one place. Then we'll capture 5. And then we also capture 7. And if you multiply all this out, you still get 210. Okay, so now we have 15, 2, and 6. Well, notice that 2 is, by definition, a factor of 6, isn't it? 6 is 2 times 3. So we really don't have to worry about the 2, right? Because if something is a multiple of 6, it is also, by definition, a multiple of 2. So now we have 15 and 6. So could we just do 15 times 6? Well, sure, we could. But guess what? They have another number in common, don't they? They have a 3 in common. So let's see if we can build our LCM. Well, we're going to put that 3 in there. And then we also have to put the 2 in there. And then we also have to put the 5 in there. So we have 3 times 2 times 5. That's 6 times 5, or 30. So the smallest number that is evenly divisible by 15 and 2 and 6 is 30. Another way to think about this, if you don't like thinking about it that way, is we could, again, just go do the prime factorization of all of these numbers. So then we go to build our LCM. So I have a 2 here, so I write that down. I have a 3 here, so I write that down. And then I have a 5. Again, 2 times 3 times 5 is 30. Notice that the process for finding the least common denominator is exactly the same as what we've been doing, finding the least common multiple. So, in other words, if you can find the least common multiple of 2 and 3, then you can find the least common denominator of 1/2 and 1/3. So, in other words, if I want to do 1/2 plus 1/3, right, I literally have to find the least common multiple of 2 and 3. And hopefully, by now, from watching this video, you know that it is 6.